Welcome to the wonderful world of physics. This is chapter 26, section 4 on magnetic force on a current. An electric current, such as one in a wire, consists of charges in motion. So a current in a magnetic field should experience a magnetic force. You'll look at the picture that I have right here, and we see a straight wire in a magnetic field B. The charges in the wire are moving, and if there's a current, then the charges share a common drift speed or drift velocity. And so each charge experiences a magnetic force that's given by this equation. So we have, remember from a previous section, that the force on a charge is the charge times the speed, the velocity actually, vector, and that's going to be the drift velocity. Cross product with the magnetic field. If the wire has a cross-sectional area, we'll call it A, and it contains N charges per unit volume, then the force on all the charge carriers in a length L of the wire is given by this equation. So here we have the force is, and if you go up here, you can see N times volume times the charge of a single one. And that N times the volume becomes N times the cross-sectional area times the length times a charge times the drift speed. And this entire thing right here is the current. We learned that in chapter 24. So what we get is that the force on a current is the current times the vector length, the vector L, I'll explain that in a minute, cross product with the magnetic field. And we're going to define the direction of L as the direction of the current. So its magnitude is the length of the wire that's in the magnetic field, and its direction is the direction in the current. So I want you to see the relationships between the relationship between this equation that we had in a previous section, that the force on a charge is QV cross B. And now the force on a current is going to be IL cross B. Notice, just as when we were talking about a single charge, that the force is perpendicular to the current, and it's also perpendicular to the magnetic field. Just as when we learned in a previous section, the force is perpendicular to the velocity. And you can practice your right-hand rule right here. We practiced this in a previous section where we took the velocity vector that the charge was moving. Well, now just replace that with the current. And so if you use your right-hand rule, you should get that the force on the wire is coming out of the page. An example, conceptual example in the book, magnetic force, a power line. It says a power line runs along Earth's equator, where the magnetic field points horizontally from south to north. The line carries current flowing from west to east. What's the direction of the magnetic force on the power line? So there I've drawn a compass directions right there, and the magnetic field runs from south to north. That's the direction that a compass points. And the current runs, it says, from west to east. To get the force of the wire, use right-hand rule, and you can see that it comes out of the page, which in this case is going to be up. And then we want to know what is the magnitude of the magnetic field, or the magnetic force rather. Well, at the Earth's equator, the magnetic field is 30 microtesla, as it says in the problem. And then it says, let's say that the power line carries 500 amps. What is the magnetic force on a kilometer of the line? So we can say that the force it's the cross product of IL and B. So as a magnitude, that's going to be ILB sine theta. So 500 amperes times the length, in this case we're talking about 1,000 meters, times the strength of the magnetic field. It's a 90-degree angle, so the sine theta goes to 1, and we get 15 newtons of force that's actually pulling up on the wire. Here's another example. You look at the picture that I have to the right. Let's say we have a rectangular loop of wire that is supporting a mass M, and it hangs with one end in a uniform magnetic field. Just one end. The lower end is not, the lower side is not in the magnetic field. We want to find out what current is needed to balance the weight. So first you think just the right-hand rule, can it actually balance the weight? And I want you to see, using the right-hand rule, that if there's a magnetic force on this, the top end, but not on the bottom end, use the right-hand rule and see that if the magnetic field goes into the page, and let's assume that current is going to the right, then the force should be upward. Now, there's also a force on the left side and the right side. So on the left side, the current going upward, you should see that the force on this left side is going to point to the left. On the right side, if the current is going around the loop, the current is going down, and so you can use the right-hand rule to find that the magnetic force on the right side is to the right. So the left force on the left and the right force on the right, they're actually going to balance and cancel each other out. So we have an upward force. But now we want to see how much does that current need to be so that that magnetic force pulling up on it is going to balance the weight, the mass that's hanging off it. So we can say that the magnetic force is equal to the weight, and the magnetic force is I times B times the length, and we're going to give that length A. We're going to designate it as A, and that equals the weight, which is mg, which means the current needs to be mg divided by the magnetic field divided by the length A. Now let's get practical. Let's plug in some numbers. Let's say it's a 10-gram mass. Let's say it's a magnetic field of 1 Tesla, and let's give it a length of 20 centimeters. So this is something that we could set up in a laboratory without too much difficulty. You plug in the values, and you get current is roughly 0.5 amperes. So half an ampere would be enough to support that 10-gram mass. All right, that's a pretty short section. That's it, section 26.4, magnetic force on a current. Have a great day.